All right. So sine theta equal to 1/2. That is on the unit circle, right? So we could use the circle, or we can use the inverse functions. So let's do part A first. Let's go ahead and use the inverse functions because it doesn't have to be equal to a nice number that is on the circle. So sine inverse of sine theta is equal to sine inverse of 1/2. So theta is equal to sine inverse of 1/2, which will give us, let's just do degrees to keep it simple. 30 degrees. Okay, so that'll be my first theta. So on exam 3, a lot of you forgot that T's come in pairs, right? So the other one would be 180 minus what you found here. These are my two solutions within one period. Okay, so let's now the new step would be applying that to all solutions. So we know that I can go around and around the circle forever. So there's an infinite number of solutions by landing on this spot forever, right? So theta 1 will be equal to 30 degrees plus 360 degrees times some k constant, where k is an integer. So in math books, we say k is an element of z. If you want to use I, that's fine, but z is a convention for integers. When I use plain English, that's cool too. K is an integer, which means -1, -2, -3, 0, 1, 2, 3, right? Okay. Theta 2 will be the same thing, just tack on that piece.
You said that K is an element of Z,
Mhm.
and Z is
In plain English, any integer.
K is an
Right. That's all it is.
So Z is what your universe, or all elements in the universe.
Right. Z is the set of all integers.
Okay.
Like R is a set of all real numbers. Q would be all fractions, etc. They all have their own special letter, but who cares, right? So anyway, what I recommend is find it for one period and then just tack on that piece. Sometimes this could be condensed. It depends. Okay, but anyway, that's the main idea there. Any questions on example 1?
I have a question.
What's up?
So then what was the one period that we saw?
One period solution is just these two. So since I only go once around, that would be k equal to 0.
You put 360 because of 2 pi?
Yeah. So instead of 2 pi, so you could say that, or 5 or 6 plus 2 pi k. This would be what, 5 or 6. Yeah. If you want to use radians, you can. Either way, doesn't matter. Okay, the same thing. This time, let's go ahead and use the unit circle. Where is cosine equal to negative square root 2/2?
45. 35.
It is one of the middle angles, but not 45, because that one's positive, right? So it would be quadrant 2 and quadrant 3. What angle are those?
It's gonna be 135. 135.
35? Okay. Those are part A. And the other one? What is theta 2?
135.
On the circle? So for cosine, it should be minus, well, you guys don't have a circle in front of you. Where is cosine negative square root 2/2? Yeah, I think that's it. Yeah, that's all we're doing. So part B, somehow says find all solutions. So that's one period. So you only have 2 answers when you go around the circle once. Part B,
I have a question. So for cosine, it's gonna be 360 minus whatever the angle we're taking. So the first one, we took 180 minus 80, and the second one is 135. So if we say 360 minus 135, it's gonna be 2025.
Yeah.
So,
Yeah. Cosine has, yeah, a different rule. All right. So for part B, oops, theta 1 just tack on that 360K. That's it. Any questions on that idea?
Yeah, go back a second and talk about that rule for cosine that I.
Yeah, we're gonna do it on the next example.
Okay.
We'll do the next one. But right now, we're using the circle to keep it simple. And then we're gonna do something that's on the circle, which requires that rule.
Why did we choose 135 and 225?
Those are 2 solutions within one period that give me negative root 2/2, right? Or is this not right? I don't have a circle in front of me.
What is,
One circle, right?
Yeah, one revolution around the circle. So if you keep going, you have more. Each time you go around, you have another set of solutions. So we have to limit to one revolution. Okay. So this means, right? This means one period here.
So I have another question. The output for Q, sorry, theta 1 and 2, where you do the 360 times K, doesn't that sort of imply an infinite number of revolutions?
Yeah, so for part B, if they don't have a restriction, so that means you have infinite solutions. Yeah.
All from all, oh, right. all-
So on part B, we tack this on to account for every single one in the negative and positive direction.
It's always going to be plus 360.
For sine and cosine, yeah. Sometimes you can, this would be the safest choice, but sometimes there's an alternate option that also works. But yeah, 360 is going to be fine. Okay. Any other questions on this?
Don't we add that together? Right?
No, that's it. We're done. Let's do the one that's not pretty, not on the circle. So like the first example, we use inverse functions on the sine, now we'll do it on the cosine.
Why are we using that?
Because you have no choice, because it's not on the circle. There's no way to know which angle is going to give me 0.65. But I have no choice but to do this. So now theta will be equal to, on your calculator, the first theta would be in radians, 0.86. So I didn't use degrees. So to find the other one, what you do is you subtract from 360. So, or in this case, since it's in radians, from 2 pi. So this will give me the other solution. 2 pi at about 6 point something. Round to 2 decimal places, that's 5.42. So that's how you do a cosine. Right, so this is part A. I didn't label it, but it's part A.
So that's sine and that's cosine.
So let's go back a page. When you did the sine, right, you did the same thing. We got a solution, but we subtract from 180, right?
Right.
So now we do a cosine. We do the exact same thing, but that's the solution is subtracted from 360 instead of 180.
How come on the first one we use inverse when just 1/2 is unison?
Just to show you the rule for sine. That's the only reason. It was not necessary. You're right.
And then when we're doing these, we can approximate if we get numbers like that.
Yeah, we have no choice but to round because it's not on the circle. It's not one of the pretty answers. So here you'd have to just tack that on. So 0.86 plus 2 pi k.
How do you look to use 2.5K in this example?
Well, let's think about it, right? Let's look at the circle, the main idea, right? You share. So let's pretend it was a pretty net answer, right? You guys see this? So if it was cosine equal to 1/2, the answer would be 60 degrees, right? So I would add 360 to get back to there again. So right now we have an answer of cosine equal to 0.65. So 0.65 is somewhere, doesn't matter, right? I don't really know where it is, but it's going to be the same idea. I'm going to add 360 to get back to that strange spot. Like, it's not 60 degrees, it's going to be like, I don't know, 47 plus 360. Does that make sense? So you find the location, doesn't matter what it is, but I want to get back there. So I add 360 over and over again. So whenever you solve one, you will add 2 pi or 360. It's the only way to get back to that answer. Whether it's exact or estimated or decimal, it will be the same. Any other questions on example 3?
Wait, so if 165 is not a unit circle, then we did the inverse. 186 is not a unit circle either.
0.65 is on circle, but it's not one of the known angles. Like if we use your calculator, let's use degrees so you can see it better. Radians is hard to see, hard to imagine. Think about it. So it's about 49 degrees. Yeah, that was just a lucky guess. So you see that? Where is that glare? So it's on the circle, but it's not 30, 45, or 60, 90. So when I say not on the circle, I mean it's not one of the pretty spots. It's in between, which it's real life, right? It's a little messy, but we got it. So this angle, 45 degrees, 49 degrees, or 0.86 radians, is on the circle. If I want to get back there, I add 2 pi radians. Does that make sense? Or
Does it scale closer to another degree?
what do you mean?
186 instead of 165.
But 165 would be the x value. This would be the angle that gives me that x value. Okay. So if I plug in 49 degrees and then cosine, I'm going to get this. Okay. Let's move to equation, other or more complex equations. All right, so far they were already isolated for you. If you notice, it was just like cosine by itself. So now you may have to factor or isolate the trig function. So do basic algebra and get sine by itself, and you're going to end up with the same question we had on example 1. Right, if I add the 1 to both sides, right, I get here. I divide by 2. So we already have the answer, right? So that was, what did we get on example one? 30? And 150, right?
Yes.
Sorry, I'm a little distracted today. Okay.
So what do you show? What we get?
Example one. It's the exact same question once you isolate sine. So there's no reason to do it again. Okay. You guys cool on this page? I'm gonna turn the page and we'll do something a little more difficult. You guys remember how to factor? Right? This book assumes that you're a pro at factoring. I don't know if that's true though.
What to say about assumptions.
Yeah.
That's supposed to be cosine inverse. or-
Cosine, it's supposed to be a 2, but I wrote it all weird. Cosine squared.
Can you remove those signs out of these effects to do this?
That's what we gotta do. We gotta factor it to solve it. But are you talking about substitution?
Right.
Yeah, let's do that. That is always an option. Just so we don't have to look at it, right? Looks all weird. This looks familiar, right? Done this. You have done this many times in the past. Now, you can factor any method you want. Doesn't matter to me. Whenever I see a number that's not a 1 here, I like to do AC method. If you want to do something else, that's fine. Have I mentioned AC method? I don't remember. I don't think. So AC gets its name from the general form of a quadratic. Right? So AX squared plus BX plus C. So what you do is you multiply the A and the C, which in this case is 2 times 3, to get a 6.
Slide divide. Slide and divide.
Slide and divide. I don't know what that is, but that is welcome if you want to use it. Is that what they call it?
Yeah, that's what lemons call slide and divide.
Oh, okay. Yeah. Whatever. So, yeah, use that technique, and we can break down that middle term. Yes.
Is it? Don't ask me how I got this because I have no idea. Is it 2 cosine minus 1 times cosine minus 3?
I think it might be. Sounds right. So let's see. So
That's 7.
7, yes. So we look at the factors of the 6 and see which one adds up to the middle term. But there's also negative versions. There'll be 6, 7, -7. I don't know why I wrote that twice. Yeah. Okay, so that'll be sum at time. So we'll choose the middle one, right? So the middle one will break into minus 6w minus w plus 3. Do your factor by grouping. First two terms have a 2w in common, giving you this. These have nothing in common, but we can factor a -1 to force it to look the same. Now pull out w minus 3. We should get what you were saying earlier. So set each part to 0 and change back to cosine because w is made up. And we have done our factoring. Now we can solve. If you have any questions on the factoring, I'm not going to spend a lot of time on it, but just in case. All right, sorry. So we'll solve for cosine, and we get this. This should be clear that there is no solution. So we're not going to worry about it. Cosine will never be equal to 3. It's between 1 and -1 forever. Right? That's the range of cosine. So there is no angle that will give you a 3. Cosine theta equal to half, there is 2 solutions, right? So theta 1, where is cosine equal to 1/2? $60? Yeah. 300? Yep, sounds right to me. Got the pi, dang it. Yes.
You see where it says 2w, w minus 2 minus 1, etc. How did you get to step after the factor?
Here?
No,
Here?
yeah, how did you get from there to below there?
Oh. So they both have w minus 3 in common. So factor the w minus 3 out of both. So the 2w goes here, -1 goes there.
Why did you minus 3?
I'm sorry?
Why did you minus 3?
What do you mean?
The delta minus 3.
You asking where it came from?
Yeah.
So when you factor 2w from these two terms right here, you're going to get a w, and this will become a -3. So I'm factoring 2w from only the first two to get this. So this is factored by grouping. Do you remember? It was a long time ago.
Practice later.
And there's many ways, Pick whatever way you want, doesn't matter. It's all the same to me. Okay, so once you factor, you go back to cosine, you solve for cosine. And then this part is back to the first few examples. Right, same kind of deal. Then tack on what you want. If they don't mention one period, make an assumption that they want all solutions. Okay, so on the exam, find them all. If I don't say specifically one period. Okay. Do one more for 7.4 and we'll move on to 7.5. You guys cool on this page? Just now, let's go ahead and say final solutions. 5 sine theta. That's a 5 in the front. 5 sine cosine plus 4 cosine equal to 0. On this one, we're not going to get, I don't think well, maybe some of them. When you have something equal to 0, we should always factor and then set each factor to 0. So what do they have in common? These two terms. They both have a cosine, right? So factor the cosine, and now we have a product equal to 0, which means you can set the first piece to 0 and the second piece to 0. Okay. Isolate sine, and you're going to get sine theta equal to -4/5. Okay, you guys cool so far? All right, so the question becomes for this one, when is cosine 0? All right, look at your circle, or you remember.
Isn't it 90 and 270?
Yeah, 90 and 270. So let's go ahead and tack on the 360. All right, so that's 2 solutions, 2 sets of solutions. Now look at this guy. this will require your inverse sign. We have no choices. 4/5 is not in the circle. Not a known. So theta will equal, see there. I think that'll be, you know what? I don't remember. Negative 53 degrees. Add 360. 306. So theta of 3 is 306.87 degrees. With get what? All right, so the calculator gives me a negative angle. So if I add 360 to it, I'll get the positive version. I'm gonna subtract 180. We double check everything. Right. Actually, you know what? That's nice. Sorry. Since I got a negative angle, I had to adjust. But I got the angle that's above 180. So I'm going to have to subtract 180 instead of from 180. I have forgot about that.
I think that it's just 180.
That's the rule for sine. Cosine was from 360. Yeah, so sine, make sure you use 180. Cosine 360. If you look at your circle, that's the pattern. You'll see it repeat over and over again.
So for sine, if it's greater than 180, we minus the angle that we got.
Yes. Yeah, so if you're bigger, you have no choice. So basically, this angle was the one that was the other angle. Does that make sense? Like, so if I were to have found an example 1,
Was 180 minus.
if you find this one first, then yeah, you would subtract to get this one. That makes sense?
The sine shouldn't be greater than 360 because if it was like greater than 360, we are out of the state. So
Right.
it should be always less than 360.
Yes.
Where can I be come from on maybe if I did one?
Unit circle. 9 degrees is where cosine is 0. See it? Okay,
Can we solve for cosine theta like you did with sine theta? Like two sine theta minus one equals 0. Can we solve for cosine?
for this part?
Yeah.
Yeah, I could use the inverse cosine.
Okay.
Yeah, so if you did, you'd end up getting, just for fun, right?
I was just curious how you arrived. I mean, obviously, you put it in the circle, but like with sine, two sine minus one, you arrive at
Yeah, so you would do this. So if it wasn't a pretty number like 0,
it. Sure.
you would do this. Okay, so that's pretty much it for 7.4. 7.5 is the same thing, but more complex. What's time we got?
And we don't add 360 to the sign, right?
Oh, yeah, we should have. Dang it.
Then we have 4 solutions because it's multiplied or cosine.
Yeah, we had 2 because we had two factors, and those 2 factors ended up having 2 solutions each. All right. So 7.5 is the same thing, except you will need to use your identities to help you out.
The whole is a 4 on 0.
Yeah, I posted. You can just do Sunday or Saturday night. Now that's the last homework. 7.5.
So the last part of the unit.
Yeah, no more kind of sections. So, okay. I don't know if I have enough time to do all of it. We have till 12:30, right?
Mhm.
Yeah, let's give it a shot. Example 1. So on all of them, we will find all solutions, not one period until, at least till the end. 1 plus sine equals 2 cosine squared. Find all solutions. So you want to do the same type of stuff. You want to be able to set it to 0 and factor. So when you see a cosine squared, you should be thinking, this is a Pythagorean identity, right? Remember that cosine squared is equal to 1 minus sine squared. 1 plus sine.
Also going back to like 3.
Yeah, so we're going to apply those ideas in order to solve the equation. So now that everything's in sine, I can most likely factor something. I'm going to move everything to the left side. Subtract by 2, add 2 sine squared. That will give me this. So I moved everything on the right-hand side to the left-hand side. It gives me 2 sine squared plus sine theta minus 1 equal to 0. Now we factor. So just like before, use what do you call it? Trippin slide or something? Factor slide?
Slide divide.
Slide divide, yeah, there we go.
The slide is the multiplication part. Divide is, I guess, another method
Got it. Got it. Okay, so
To be honest, I forgot that something.
the name sucks, so that's good. Something.
I guess it's good because they're video versions as they go back.
We get rusty when we don't use it. It's okay. All right, so I'll skip the factoring step. Substitute W, then you will get W plus 1 times 2W minus 1. You can do brute force, trial and error, slide and divide, square method, whatever you want. Once you factor though, you can set each part to 0. See how it becomes the same thing once you apply your identities, right? This is, once we got to here, this is the question we did in the last section. So the new step was just use an identity. So we get to here. And we should know the solutions at this point. Theta 1 will equal 3 pi over 2 plus 2 pi k. Theta over 2 will equal pi 6 plus 2 pi k. Yeah. Because they're pretty, and we can use the unit circle. And if they weren't, you would have to use the inverse.
So then the question is it sort of arbitrary that we decided that theta 2 is pi 6 instead of 3 by 2? Or does it matter like which one you live as theta 1, theta 2?
Nah, doesn't matter. Call them whatever you want.
Where did 5 by 6? We only had negative 1 and 1/2, right?
1/2, sine will be 1/2 at 2 locations.
Right.
That's what it's doing. That's what it's doing.
You know, but the period is defined, is it?
It is not. That's why we have to tack on a 2 pi k.
Right.
Why are we using ratings instead of degrees?
I don't know.
Right, but if the period isn't defined, isn't there an infinite number of thetas?
There is an infinite number of thetas. So each of these represents an infinite set of solutions. Yeah. And technically in math, there's multiple levels of infinity.
So I'm not sure I understand why there are 3 infinite sets. Why is there as opposed to infinite sets?
Math can be weird like that. So there's multiple sets that are infinite that are different sizes, which sounds strange because you feel like infinite should be one size, but that is not true.
But there, yeah.
So mathematically, we can show and prove that different sets are bigger.
Some infinity.
Yeah. So these each contain an infinite set, even though infinity is infinity, right? But they are different elements. It's kind of like comparing all the even numbers. The set of all even numbers is infinite, but so is the set of all real numbers. But those are different sizes. And there's technically infinite numbers between 0 to 1. So the numbers between 0 and 1 is also infinite. And then there's also infinite numbers forever. So, and then between each of those integers, there's infinite sets. So as you can see, the size of infinity gets ridiculous and strange. There's a whole, what's the word? topic of mathematics that just studies that. It's called measure theory. It's not my cup of tea. I don't like measure theory. I find it uninteresting. But it can be used to prove some of Einstein's theories. It's kind of cool, I guess. That part's fun. The measure theory itself is not that fun. Okay. Example 2. You guys pull on this page. So here, there's nothing to factor, right? Sine 2 theta minus cosine theta. So it's supposed to be a theta, by the way.
That's not 20.
Yeah, not a 20. Sine 2 theta minus cosine theta. So there's nothing to factor. What would you do for your sine? That's the only thing we have to work with, right? If this was squared, you could do maybe Pythagorean, but it's not. So I'm hoping you see that 2 theta and it gives you a hint. What do you guys think?
Split it up. Sine 2 plus theta.
Yeah, that could work.
Let's just follow.
Yeah, that's not a bad idea. I like ideas. It might work, but it could be complex. But since it's a double angle, we'll just apply double angles. But once you apply the double for sine, you will see that this will allow you to factor, right? But you're talking about splitting it up to theta plus theta?
Yeah.
That might.
That's what I was wrong.
I assume that's what you meant. I don't know.
Let's assume that. Okay. Let's assume I was being smart.
That's going to be my assumption all the time. Assume you're all smart, but when you turn in garbage tests, it's just a bad day. It's just what I like to tell myself. Okay, so as you can see now, there's a cosine in common, right? So once you factor, you're pretty much good, right? We're back to those first 2 examples. See what I mean? We're doing the same thing again. So we just got to get there. So you may have to find, so all those identities we're doing, all those proofs, we can now use those skills here for something, not just for fun. Got my theta though. So let's state the solutions for cosine. Yeah, same thing, right? It's not too bad, right? I hope. And then this we did like already 3 or 4 times. What was that again? I6, which is 30 minutes, and 150. Okay, so if you can factor outright, do it. If you cannot, see if there's an identity that can help you. Sometimes there's nothing you can do. Which would be the next example. Any question on example 2? So look at this one. There's no squares, there's no double angles, there's nothing that's in common. So you're kind of just stuck. So what you have to do is force the problem. So when you're in this kind of scenario, square both sides and start using identities that come with the squares. So when you square it, then you can do Pythagorean theorem, etc. Okay. So remember, sine squared theta is equal to 1 minus cosine. So let's go ahead and change it since we have a bunch of cosines on the left. Move it over. Do you remember in algebra when you would square both sides? Do you remember what would happen? When you try to solve for x? Like sometimes you would get, I don't think we did it. Sometimes you would get solutions that are not true. You get, because when you're squaring something, you're adding extra stuff to something that was not there. So that means you're going to get extra solutions that don't belong. We call those, the math book calls those erroneous solutions. So whenever you square both sides, you're basically creating a new problem that didn't exist to begin with. So you're going to have to check every solution to see if you have a fake answer. Okay. That's the downside for squaring both sides, because when you square, you notice, oh, I can do all kinds of stuff now, right? But the downside is you may have a fake answer somewhere, but we'll get that in a second. So I'm gonna move everything to the left side. So give me this. The ones will cancel. Cosine squared plus cosine squared give me 2 cosine squared. So yeah, just factor cosine, we're good. Looks like, oh, hold on, there's a 2 in common too. So factor 2 cosine theta equals to 0. Cosine theta plus 1 equals to 0. That 2 isn't really going to do anything. We divide both sides by 2. Do you agree that it will be gone? So why even worry about it? Over here, so let's not write the 2k stuff yet, 2 pi k. Just find the answers. Cosine is 0 at pi over 2. Three pi over 2. And -1 at pi. And that's it.
Those are the ones where cosine equals 0.
Yeah, these two, it's 0. And this one is for this guy here, -1. So we have 3 possible solutions. So we need to plug them into the original and see which one's fake. Okay. Maybe they all work. I don't know. It's possible. Maybe not. So let's do pi over 2 first. The cosine of pi over 2 plus 1, is that equal to sine of pi over 2? Is 0 plus 1 equal to 1?
Yes.
So this is a true statement. Pi over 2 works. Now let's try 3 pi over 2. Cosine of 3 pi over 2 plus 1 equal to sine of 3 pi over 2. Punch that into your circle, calculator, whatever. This will be -1 plus 1 equal to -1. I'm sorry, this is a 0. 0 plus 1, is that equal to -1? So this is the false answer for sure. So we're not going to use that. That's my 1, 2. Sorry. Yeah, it's supposed to. This is actually 0 now. I'm trying to fix it. Cosine of pi plus 1 equal to sine of pi. Is -1 plus 1 equal to 0?
Yeah.
Then we're good. So it looks like only theta 1 and 3 were the solution. Feel weird calling it 3, but whatever.
So just to make sure I understand like the applied mathematics,
Uh-huh.
we're basically proving that the angle is the same at each solution of cosine and sine.
Yeah, we're trying to show equality by plugging it in. Because if we have equality, then it was a solution to begin with.
So
Yeah.
why is it that the answer is saying,
It needs to be, right? Because we have an equation.
no, 0 plus 1 is 1 supposed to be -1?
Here,
It's the same.
0 plus 1, is that equal to -1?
No, why is that the negative? Is it because of where it is?
When you plug this angle to sine, you will get a -1. So all these numbers came from the circle, right? So then we check, is it truly equal? And if it is, then
So I have to bring in the negative that's on the circle, even though I don't see it.
yeah. Well, look at your circle, 3 pi over 2, -1, right?
Right.
That's. See it? The bottom?
Zero. Wait, yeah.
Yeah, it should be 0, -1. So the y value is the sign. So that's where this came from.
Okay.
So this is all coming from your circle or your calculator, depending on what you're using. So you only have to check when you square both sides. That's the downside. Okay. There's like, sadly, we're out of time. The last question was the hardest one, which will be on your exam. So I guess we'll talk about it Friday. Friday, we'll do one last example, and maybe we can review or do some practice problems together, something like that. I don't see you. Good luck on your exam. I'll be posting it today or tomorrow. So it's a take-home exam, so just do it as soon as you can and upload your work. Please make sure that your work is perfect. All right? If it's a take-home exam, take your time and do not turn in garbage.
When is the exam?
I'm not sure yet. Today or tomorrow, it should be inside Canvas. Just download it and fill out every single problem.
And then you want it, okay.
So you
And
upload,
just
you
send
will,
it back as a,
yeah, you'll have a location to upload your PDF. It's a Monday night, the latest. After that, I'm not allowed to assign things, so if you don't turn it in, you're SOL, I guess. All next week. So probably Monday, Wednesday, Friday. Well, yeah, Monday, Wednesday, Friday.
yes.